And got it. All right, so I'll share my screen and someone give me a thumbs up if they can see it. Excellent. All right, so welcome everyone and thanks for joining. So I know that this topic, it's one that I proposed actually when Crystal and I met, and she invited me over to maybe talk with this Our Ladies chapter, which by the way is a great initiative in general, and I like that it's a very active chapter. And I proposed regular expressions because at the time I was developing teaching materials for that, for various courses that I sometimes teach or facilitate, and it was something that I more or less not really mastered, but something that I use a lot, and I wanted to make some notes for myself and for others. So that's why I propose this topic. We will define everything, and hopefully, regardless of your experience level with these things, everyone will benefit from today's session. So as I said earlier, feel free to just drop your questions or answers to things I may be asking in the chat, or maybe if you want to chime in and unmute yourself, if the permissions allow, just go ahead and I'll get started. So a little more about me beyond what was introduced by my host. So these links on the slides are live links to my social media profiles and my GitHub, my personal blog that has a lot of R material on it, and my email if you wanted to get in touch with me afterwards. So as I was introduced, I am a biologist by training, especially a mammalogist. So I study mammals, do things like conservation and ecology. Biogeography, I like to do a lot of mapping with R. And this was also mentioned, I am a certified trainer. So I do have some courses that I teach year round, or I am available to teach or facilitate courses if needed. So my contact details are around there, and we can get started with regular expressions. So I guess the first thing to do is to define what are regular expressions. You probably see a lot of different ways to refer to these things, like regex or regex or RE, or maybe the singular or plural way of writing them. It's all the same to me. I think it's all the same to anyone. So I'll be using these terms interchangeably. Most of the time it was for space reasons on the slide, so don't worry about that. But so let's actually define these things and maybe justify why we're all connected here tonight. So basically, regular expressions are on its own right a concise language, a programming language to describe patterns of text. So it's a kind of a mini language that lives inside other programming languages, including R. And I guess another more informative definition would be that regular expressions are specially encoded strings of a bunch of different characters that will match patterns in other text strings. So in practice, as I was saying, regular expressions are a computer language. It has its own terminologies and rules and syntax. And what essentially happens is that we create a regular expression just as a string of text. And then when this thing runs behind the scenes, it compiles into a miniature program, basically as if we were writing custom software to go into an input string and just find the pattern. And ultimately, what we can do with this is to either match a piece of text or maybe search for something specific, replace a match, or maybe split some piece of text. And this can really be useful in any of our workflows when we're working with R. So first, I wanted to just to get an idea. Have you used regular expressions in the past? If so, what for? So maybe I'll have a look at the chat if I can see it up here, or if anyone wants to chime in. right, so two people already are mentioning, cleaning stuff that comes from elsewhere, like addresses, street addresses, maybe even email addresses. I see Robert mentioning them about using regular expressions. Any other use case that someone's familiar with? So things like, as a few people are saying, like match and replace, clean data, work with response text boxes. So I'll move on. And in general, so we did get a bit of an idea of what these things are for, right? So basically, we're finding and replacing or cleaning things, or maybe we have words with various different alternate spellings because people will input a different, a word with a specific spelling 100 different times. This happens with country names. This happens with state names. This happens with things like American versus British spelling. So we can work with text, and we can make the process of describing patterns and then finding them in whatever our input is, and then cleaning that up. We can really streamline that by learning a few basic things about regular expressions. So as I said, even though we haven't really gotten into it, regular expressions, we use those to match patterns, right? To describe a pattern, or if we want to match pieces of text, we can do things like maybe match only the singular version of a word like dog, but not dogs, or maybe also refer to the position of our pattern along a chain of text or a string, or maybe alternate spellings of the same word as I was mentioning. Again, the position of our matches within a string. We can maybe exclude digits, exclude a few particular letters, maybe match dates in different formats like date and then a forward slash and then the month and then a forward slash and then a year. And we can specify very flexibly a format like that. A few other patterns that we can maybe describe using regular expressions, things like zip codes, or maybe if we have a cell or a value in our object with data, and we have, I don't know, a value, and then next to it some uncertainty or the standard deviation, and we just want to clean that, or we want to extract that and put that elsewhere, and the values are inside either square brackets or just parentheses, we can match those things regardless of how many of whatever sits between those brackets. We can match those. We can do things like match valid Twitter handles. So it's things that start with the @ symbol, no spaces, no symbols, and they can only be 16 characters long at the most. We can also do things like work with letter case. So it's endless patterns that we can, but basically if we can describe them just verbally like I'm doing here, we can most likely write a regular expression to match these things. And then on to why are we doing this? So I do believe, and I think other people believe that would agree with me, is that learning these things is quite valuable skill, because we will ultimately save time when we need to match or extract or transform text. Often, once we learn these things, we can not only save time, but also replace, really shorten our code, and then understand what other people are doing. And the good thing about this is that regex is not specific to any programming language. So R comes with a regular expression engine built in. Python has one, Ruby has one, Java, Perl, all those things, they come with regex engine, and it's basically the same. There's very little change. If we learn them in R, we can use them in Python and whatever. There's sometimes search boxes in websites that they'll allow for regular expressions. So we can also do that inside things like web services. And again, these are the kinds of things, kind of like either automation for a task, or maybe that thing where we create a plot and we can either tweak it with code, or we can just open it up or maybe edit that in a graphics software with a mouse and just clicks. So in these kinds of things, we do want to get good at regular expressions so that we're comfortable being either the cat in the box or in the purpose-built bed for it. So it's that kind of thing where I think the more we learn, the more comfortable we are in either of these things. So sometimes in things like maybe finding a term and replacing it, we can just use an interactive tool, either on even in RStudio or another IDE to do things manually, or maybe we can just come up with a very flexible, very quick regular expression that will help us not write the same query with minor variations over and over again. So to work with regex, we need two things, basically. We need strings, so we need text that we're working with, and we need patterns. And then what we'll do is that we'll describe a pattern, and then we'll look for this pattern in some sort of input string that we're working with in our data of interest, right? So I've been mentioning strings a lot, so I might as well define them and specifically define strings in the context of R, right? So strings we can define, I think, as maybe a collection of characters that make up one element of a vector. So maybe here we're assigning or we're creating this object called test string. It's an item of type vector, so it's just a character vector. We have things enclosed in quotes, and it just says this sentence is a string. So it's just a collection of characters. And then in R, we can also have multiple strings in a character vector, right? So each of these things, like these things enclosed in quotes, like dogs, cat, parrot, pig, each one of those is a string. And then all those strings were concatenated into a character vector. In this case, it's something called pets. So these are the kinds of things that we'll be operating with. We don't necessarily need to be working in R. We don't need to be working with vectors, but at the same time, in R, strings are everywhere. So the name of an object, row names for maybe a data frame or table or data table, things like that. Row names are strings, variable names are strings. Anything that isn't numbers is basically a string. So we can use these tools to look for patterns, to try and match things either inside cells or values, or maybe row names, variable names. So because strings are everywhere and we can work with strings using regular expressions, that's why it becomes very, very handy to know these things. So a quick note here, because this has tripped me up in the past. I've seen this trip up other people as well. So in R, strings or just text in general is case sensitive. And this means that uppercase and then lowercase letters, these get treated as distinct entities, I guess. So for example, in this case, we're testing the equality between rat and then rat. We have both of these strings in all lowercase, so we have identical objects, identical strings. But then if we have rat in all lowercase and then rat with a couple of uppercase or capital letters in there, they are not interchangeable. To R, these are two different characters. But fortunately, we can work around these things. So by default, in R and in most contexts, searches done through regex are case sensitive. So we have a few options that we can do. We can sorry about that. Yeah. that someone knocked at the door. So I was talking about, oh, okay. So case sensitivity inside regex. So we have three options that we can talk about. So we can either build regular expressions that are case insensitive. So in that case, I don't know, uppercase T and lowercase t, that's interchangeable, it's fine. We can also turn on or off case sensitivity. And the last option, which I don't really recommend, is to either standardize or modify our input text before we do anything with that. That's not very useful, but it's something that I've seen done. So I just mentioned it here in the slides material. So we are just about ready to get started. So this is what we'll be doing. These are the 3 steps for actually working with regular expressions. So what we need to do first is describe a pattern that we're interested in detecting or doing something with. We provide an input string that we'll be working with. And then these 2 things, we feed that, especially in the context of R, into a function that will take a that will accept a regular expression as an argument. So these may be the types of functions either built in with base R or through any external packaging to do things like matching text or maybe replacing text, splitting strings, anything like that. And then, so the matching itself, everything, this gets done more or less behind the scenes by the regex engine, which, as I was mentioning, is something that gets built in and installed, and it works within R. And we don't really need to bother with this. We don't access this engine directly. But any function that will take a regular expression as an argument, we'll just call on this engine whenever we need it, right? So can anyone either just mention, or maybe in the chat, any function that you're familiar with that will take a regular expression as an argument in R, either in base R or any other packages that you might use? Can I have some examples, please? I'll open up the chat. So I see grep and grep-al, or grepl. I'm not sure how I meant to say. So yeah, those are the pretty old school, very useful base R functions for matching patterns, or maybe even replacing whatever we matched. So thanks, Megan, for that. Crystal was mentioning all the string R functions. We will be discussing string R later. I see another one, str replace. Someone's mentioning the paste functions. I'm not sure if they take regular expressions they might, I'm not sure, in any of the arguments. But yeah, I see that at least some of us here are familiar with the grep or grep, which is not even exclusive or to R or native to R. I think grep or grep or those things, they come from bash, just command line scripting, because regular expressions also work a lot in command line tools like the bash or the thing that comes with Apple computers that I'm not very familiar with, or for bioinformatics. So just a toy example here about the 3 things that would happen, or the 2 inputs that we need, and maybe the output that we'll see. Just let's do a very basic matching for a pattern. So let's say we have an input string. We have this string, everything between these 2 quotation marks, right? It says the dog is fat. Our pattern of interest, let's say it's just dog, or just the characters B, O, and G. And then we could give that into the regex engine. Regex, its only task, or its calling in life, is to go and match that pattern that you described in the input string. So in this case, the match that we'll get is dog. So in this very silly, very basic example, we're searching for a specific sequence of characters. And because in this case, we're just looking for these three characters, the regular expression is just that same sequence of characters, right? So what we're saying is we're looking for a D followed by an O followed by a G, no spaces between them, all lowercase, these three letters together in this same order and reading them from left to right. So we will be working in a regular expression tester here. So if you want, and you have the slides open any of these things. So I tested that these are live links and the web pages were working at least earlier today for me. I'll be working in this one called Rubular because it's very streamlined. And it's just an online web page that will help us test our regular expressions. So I do have that open on another tab, and I'll get to it in a bit. But just take a second here to open any of these things if you want to follow along, or just try some regex that we'll be working with. And now, I think regardless of which one you chose to open, and also beyond these four ones that I recommended here, mainly because I've used them in the past, there must be dozens or maybe hundreds of online regex testers out there. There are even add-ins to have a little tester running inside our studio if you'd like to just work there and not leave your IDE. But ultimately, we get these things, right? It's just the layout might be different, but we have these things where we have an input field where we'll put in our regular expression. We have another input field for our text string and some sort of viewer that will show us the matches. So again, in this case, we're interested in the pattern, which is just the word friendly. We have a text string that actually contains this pattern. It just says that the dog is friendly. And the match is that we're only matching the sequence of characters FRINDLY. So let's do a little bit of practice with one of these testers that we had open. Hopefully, if you have the slides open as well, we can just copy and paste this text here. And I can just go to a regular expression tester. This one's the one I mentioned, Rubular. I'll make the font slightly bigger. I'll paste the test strings that I had in the slides, and I wanted just to show you what happens with a few of these things. So in this case, every time there's a line break or a new line, we're treating these things as separate strings or separate parts of the same string, and then we can try out different regular expressions. Things like maybe I'll do AT. That's my regular expression. So we will get in the results or the results pane or panel, all these matches, which is whenever we see an A and a T together in that order, anywhere along these strings. We can do maybe OUSE. We're getting a single match here because, again, as I was mentioning, of the case sensitivity. Even though we have the word there, mouse, in all caps, and we have the housekeeping just there, even though there's some characters in common, I just wanted to show the case sensitivity. Let's say, for example, we're interested in any character, any string that ends with the letters AT. No matter how long, or no matter if it's uppercase or lowercase, we will be able to write a regular expression for that in just a few minutes, actually. So just have a go. Maybe at this point, we're just doing little sequences of characters that may or may not exist within our target strings. We can do red, no matches. We can do red, no matches either. Very silly, but we will get to very cool stuff within a few seconds. But some definitions first. So as I've been mentioning, so both any string that we're working with, including regular expressions, everything is made up of characters. So characters are things like whatever we have on our keyboards. And then for regular expressions, we can classify characters into two main classes depending on their behavior. And first of all, I'll talk about literal characters. So everything we've been working, or with everything I've shown you so far, like looking for dog or DOG, where the dog is the regex, our input string is dog. We're basically just trying to get a match whenever D, O, and G occur together and consecutively in the input text. So what's happening here is that, in this case, D, O, and G in our regular expression, those are just literal characters. They stand exactly for what they are. We want a D, and then an O, and then a G, and this gets matched in the same order they appear in. Very, very straightforward. But it would be not very fun and not very useful, right, if we couldn't really describe more complex patterns. So let me say that the real power of regular expressions comes from us being able to describe really complex patterns and then just match them. So if we can describe a pattern, as I was showing earlier on with some of my verbal descriptions, we can most likely, with some maybe not quickly, but we can most likely write an expression to match this pattern. And we can't really do that with just literal characters, like typing letters sequentially. And this is when regular expressions start to look to anyone unfamiliar, that they will start looking a little bit like gibberish. So it says here, like how to regex, you open your editor, and then you just type whatever on your keyboard. And sometimes that's what regex might look like. And it might look like that because we're actually calling on the second type of characters that we can use in regular expressions, which are meta characters. So there's a tiny subset of characters that when we use them in a regular expression, they take a special functionality, or they take on a special meaning. So as earlier when I said, in the regular expression dog, the D stands for a D, and the O matches an O, and the G matches a G. In this case, there's some special characters that will have a different interpretation. There's a few others that I missed out on here, but the meta characters that we'll be using, they include things like square brackets, the hat symbol, the $sign, periods or dots are very, very useful, plus signs, question marks, parentheses, and the vertical bar. So these things, when we use them in regular expression, when we use these characters, they'll take on a unique function that actually, these are the things that will grant us the flexibility to match more complex things. And then within this more or less family of meta characters, then we have subfamilies or other groups of meta characters according also on what they do. So we have things that are very useful, things like wildcards. I'm sure but at least those old enough, we've used wildcards maybe when we're looking for files in the Windows operating system. It didn't run on regular expressions, it used a different engine, but things like the star that we sometimes use in file systems. So it's just a character that will stand in for anything else. And in regular expressions, a wildcard can be the dot or the period, and it will just basically stand in for anything else. So the dot will match any character once. So if, for example, we write a regular expression that just F and then dot L, will match anything that starts with an F, ends with an L, and has two other characters in between. So in this example, the matches are highlighted in yellow for where we would actually get a match. But let's look at this other example here where it says flail. That won't get a match because there's 3 characters, not 2, in between the F and the L that we're defining in our pattern. So that's already useful. We just type in however many dots we want, and then that's just however many matches we'll get, however many characters we'll get. So we're just matching any character once. And this other example here, we have dot top. So this will match us things like stop and then part of the word, the string isotope. It could be anything and then top. But for example, we won't get a match with the string that's just topple because there's nothing before that T, so we won't get a match there. So wildcards, they're pretty straightforward, but they're very, very powerful. So let me just stop here and see if anyone has any questions or if I'm just saying nonsense.
I have a question, Luis.
Yeah.
Are there other wildcards like an asterisk? Or does that have other meaning?
I think the dot is the only wildcard there is in at least as far as I know in regular expressions. We can do things to modify the behavior of the dot, but I don't think there's any other character that will do it, that will do the same, that will have the same behavior. So as far as I know, it's just the dot. Any other question? Well, hopefully that means no one's lost or considering that I'm just saying nonsense. So I'll move on to another cool family of characters that we can use, of meta characters, which are character sets. So to create a character set, we use square brackets in a regular expression. So what happens is that we'll match whatever characters we're putting inside the square brackets. So for example, this relates to what I was doing earlier. If we do inside a square bracket, we put the C, a B, and then the literal characters A and T will match things like cat and bat, but we won't match rat because we didn't put we didn't put an R inside the character set. And we can use character sets to match, I don't know, alternate spellings of someone's name or misspellings of a different word. So whatever options we need to match within a restriction that we can define using a character set inside square brackets, we can use that to match things more flexibly. So in this case, we have, a single regular expression that we can use to match these 4 spellings of the same name, and that maybe that saves us some time, hopefully. We can do things like negate a character set using this little hat symbol, as long as we put it inside the square brackets. So for example, if we do a character set that includes inside the square brackets the hat and then A-E-I-O-U. There's an extra letter there. It will match everything except vowels, or we can just match everything except uppercase R, things like that. And keeping within the square brackets, we can use a dash inside the square brackets to just refer to things that are sequential. So letters, if we do A-D in uppercase, it's just shorthand for a sequence between uppercase A and uppercase D. We can do the same thing with numbers. Or we can do a thing like a character range. So A through C, uppercase, and then A through C, lowercase. So that will match any alphabetical characters. So if we have the string that has numbers and we have text, and we are only interested in alphabetical characters, we can use a character range to only match that. We'll get to a bit more practice soon, but let me just do another subfamily of these meta characters, which are anchors. And these we use to match not actual characters, but actually to specify the relative position of whatever we're matching. And there's only two meta characters that we use to work with relative positions like that, which are the hat and the $. And we can just read them as something that starts with whatever or something that ends with whatever. So for example, we have the hat and then the literal characters MIL. And if this is our string, we'll get a match here because we have an M and an I and an L at the beginning of our string, which is just a single word. But if we have another string that includes MIL, but this pattern is not at the beginning of the string, so family won't be a match. Or maybe we can do the same thing, like the literal string ING, and then the $. We will get a match when this pattern here is actually at the end of a string. In this case, again, our string is just the word going. We'll get a match here. If we have our sequence here, but it's at the beginning of the word of the string, we won't get a match. So this is just another very useful family of meta characters that we can use for that. So I have some practice here, and hopefully someone can write this for me, and then we can test it out. So maybe with what we've seen so far, or what you know already, how can we match the strings? So just having these things on these words on separate lines, so with just many different strings, and maybe we can think of this as maybe having different rows in a data frame. Let's match tender, timber, tailor, and taller. So how can we match that with a single regular expression? And then second challenge here, let's try and write, or let's try and match possible misspellings of the word herbivore using character sets. So let me check the time, and let's take a few minutes to do that. I'll open up the chat to see.
Yeah, I was going to say, while people are working on it, at least there's a couple of questions in the chat for you. So.
All right.
And did you want people to drop responses in the chat?
Yeah, if someone has, or if someone wants to explain what's happening, then we can do that. And let me just look at the questions in the chat. So someone's, how can you use the option like I for case insensitive? Hold on, I lost the question because people haven't. Hold on, so I might need the askers of these questions to elaborate, because I think I understand the question, but I'm not sure.
Yeah, feel free, whoever wrote the questions, feel free to unmute and ask, please.
I can't remember when these were asked, or what was.
For The case insensitive one, I just noticed that on the quick reference, like I is listed as an option, but I can't figure out how to use it in the code.
And that's in one of these online testers. Which one?
Rubular.com. It also
Sorry.
lists other options like make dot match new lines, X, ignore white space and regex.
Okay.
And I don't know how to use those options.
So those options we won't be using when we're working in R. So, but I will explain this so you don't feel lost or whatever. So let me show you in the actual tester itself. And there's a thing at the bottom. It just says that there's a few options here that or flags, I guess they're called sometimes. And it says an I makes things case insensitive. I think we're just meant to put an I here, and it applies to. So we might, if I do this, and it was what I was suspecting. So just by putting this flag here, which is I don't know what it's meant from, where it's coming from, but if we apply this flag to, I guess I stands for insensitive. Did you see we matched both appearances of the string cat? So I think that should answer your question.
So there's no way to do that inside of R's engine.
So there is, and I'll show you in a bit.
Thank you.
And then, hold on, there's a.
Do you see the other one? There was one that says, do those have to correspond to the start end of a string or words in a string? I'm not sure what that was referring to, but.
I think that was referring to anchors. So these things. So these things are the start end of a string, the whole thing, not words. We will talk about the boundaries at the start and at the end of words. So that's actually a very good question. But these are the very start or the very end of a string, not words within it. So hopefully that there's no more pending questions.
And then there was one more question, Luis, that said, did you talk about the star? Which I don't think you have yet.
No, so I talked about the star in the context of Windows and that kind of thing. In regular expressions, the star is not a wildcard. It is a meta character that we'll get to, I think, in 2 more slides. So I will talk about the star. Just give me a minute. And now let's look at them. I think questions we're good with pending questions. So let's talk about your answers for this. So for the first little task, write regular expression to match tender, timber, color. I see a suggestion right down at the bottom of the chat. It's just T and then 1, 2, 3, 4 dots and then the R. That's the answer I was looking for. There's other things that will work. So let's just try it out. Tender, timber, tailor, taller. I think that suggestion by Marcos, that's what I would have done in this question. So just we have a T, we have an R at the end of the whole thing. I'll just set these up to be new lines so that the matches are different. And the suggestion was to do just T and then 1, 2, 3, 4, and then the R. So we will get these matches, and we can do things like taller. And we won't get a match because we have a specific number of wildcards that were of unknown characters that we're matching. So that's one way to do it, and that's the way I was aiming for, at least in this context with what we've learned so far. And then let's try the other one, which is just possible misspellings of herbivore. So I'll do the possible misspellings of herbivore. We can do that. something like that. So we can use the character sets that I was mentioning earlier, which we do with square brackets, right? So we can do just literal strings here, HER. Any suggestions? By the way, when I have the chat open, is it? Can you see it on your screen? It's something that I've never been sure about with Zoom. Okay. Did anyone figure this out? So someone's mentioning there's a character set with a V and a V. That's Toyin Ola. That's what I'm looking for. So inside a character set, the order of the things we put in doesn't have to be alphabetical or whatever. So we can do things like her, and then a V and a V, and then another character set. We can do a V and a V. Or so in this case, hopefully you all can see it. Using these character sets, which are basically the same one, because the order doesn't really matter. We're matching these alternate spellings of the same word. So that's what I was aiming for, and I did get one of you to suggest that particular character set. So that's great. Quick multiple choice question, so you don't have to type. So how can we match, or actually, which of these regular expressions will match food at the beginning of a string? It's just a quick memorization, and you can just refer to the slides. And a bunch of people are saying A. Right, so we have the hat, which is the start anchor, and we have the start and then the literal string food. That's right. So we would get a match possibly with just this one here, but if we're looking for it specifically for this pattern to be at the beginning of the string. So that was good to see a lot of quick responses to that. I've heard some people say that they get these two confused, and there's some little memorization techniques about first there's the thing, and then you get the money, and then so the dollar sign is the end anchor. It's just easy. I memorized these two options. You will at some point as well. And we are now at the asterisk that someone was mentioning, because we can actually apply these quantifiers to modify our searches. So let me just read my definition here. So we use quantifiers as to specify how many times a character or character class that we used, how many times a character or character class must appear for a match to be found. So we have all these quantifiers. These are harder to memorize, but it's easy to, some of the testers have a quick reference guide at the bottom. You can use this slide here. I think I sometimes write this down and then just have it on hand. So we can either match 0 or 1 occurrences of something. We can do 0 or 1, 0 or more, or 1 or more. So it's question mark, asterisk, plus sign. And then we can even specify with a number, just a specific number of occurrences. And then an important thing to know here is that quantifiers, they'll apply to whatever's on their left, so whatever precedes the quantifier. So let's just go through some examples. So if you recall, the question mark, which is the one at the beginning here, it'll match 0 or 1 of whatever precedes it. So in this case, we have the literal string model, then an L with a quantifier. So in this case, we'll match either 0 or 1 else. So in this case, we're matching with this regular expression, we're matching both spellings of modeling with either 1L or 2. That's a good use of the question mark to match either 0 or 1. We can go beyond that and use the asterisk, which is not a wildcard. In regex, the asterisk is a quantifier or a star. So in this case, because it's following the literal character A, we're matching Y, and then either 0 or however many A's we can find after, followed by another Y and then an exclamation. So we'll match things like just YY or yay or yay or yay with however many A's we choose to type, right? So we have 0 or 1, 0 or more. Then the plus sign, that's 1 or more. In this case, the plus sign is after the literal character O. So we're matching no with however many no's, except if we just have the letter N, because we're looking for at least one O here, we won't match that. Or we can actually just specify how many times. So in this case, we're looking for 2 E's. So we have the E, and we have a quantifier specifying 2. So we'll have things like keep and be. But if we only have 1 E on its own, we won't get a match. So that's a very, very useful thing to do. And the thing is, we can combine these things. So let's just, before we get to combinations, let's just try and do a quick exercise here. So with the quantifiers we just saw on the slides, let's try and match all these spellings of cute, right? So I'll just put that in my tester. Maybe we have a get carried away with the U's because of whatever reason. So remember that we want to apply a quantifier, in this case to the letter U, because we want to match all these things here. So which quantifier, or which quantifier would you suggest that I use here out of the few that I mentioned? So someone is mentioning the plus sign. That should work. Because if you recall from the slides, let me just go back. And it did work because we have all these matches highlighted. The plus sign matches 1 or more. So we will match just cute, but we will match also however many U's we decide to type. So I can just keep adding U's and we will still get matches. We could possibly use the asterisk for this. And that works as well, so quite flexible. And it's not that big of a deal if it works, we can use either of these things. So yeah, let's do the plus sign. Because we were matching 1 or more occurrences of whatever we had beforehand, so that was the letter U. So that's first little question answered. And then I see someone already answered the second the little multiple choice question, right? Which is how do we match all these things of computers. So they're just plural and singular and uppercase and lowercase. And someone saying that the answer is letter A. Jules, would you mind explaining your answer for everyone?
Sure. So to begin the brackets, you're saying that you're going to allow either lower uppercase C,
Yeah.
and then the S question mark allows there to be an S at the end or not. And then the umputer is the same across everything.
Yeah, so I'll just go back again. The question mark is for 0 or 1. So I use the question mark a lot sometimes when we're working with things like singular or plural, because there can either be an S or no S. It's just, we're getting more flexible with what we can describe, right? So that's very cool. That's a good explanation, Jules. Thanks for that. And I'll keep going. A few more tokens left to go. This one I don't use that much, but it's worth knowing. So alternation. So it's just either this or either that, separating a series of alternatives. For that, we use the bar character. So we can do just outright put two literal strings like dog and bird, and we alternate that with the vertical bar, or we can do things like enclosing the alternation in brackets. Also use that to almost as a character set to match, I don't know, American and British spelling of the word gray. And then we have this one is an important one to know. So it's the backslash. So it's a very special sequence, and it's sometimes that we refer to as an escape. So it has two actual purposes. If you see a backslash in a regular expression, it can either signal that we're using a shorthand sequence, or they're just a few abbreviations that we'll go over. So they're built-in abbreviations or built-in sequences that just help us build regular expressions faster. Or actually, it will just give whatever special character we're using, like the question mark or maybe an asterisk. Maybe we are looking for an asterisk. We want to match an asterisk. We don't want the star to have a special functionality. So we, as we say, we escape it with a backslash. So let's say we want to match hello with a question mark. We don't want the question mark to behave as a quantifier. So we want to treat it as a literal character. So we put a backslash. But then in R, we have to escape the first backslash first. So just when in doubt, just have two backslashes. Also, if we put any of our meta characters inside a character set, we strip them of their special nature. So if we want to match a dot, we escape it. If we want to match a plus sign or a question mark, just escape it with backslashes. So this is a somewhat recent tweet. Garrick Aiden Dewey, he works at our studio or Posit now. He's really good at this, and look at his tweet. He's just saying that just keep adding backslashes until things work. Because things like new line operators, which is the \n, we want to match those in a string, then we need to escape the first backslash and then escape the other backslash. And then, as he said, just keep adding backslashes and it will work. But I just wanted you to know about escapes. And these are the other uses of having the backslash. So maybe if we don't feel like writing a character set, or we want to, they're like just predefined or pre-cooked character sets. So if we use \w, it's for what are called word characters. It's basically just having a big character set where we're defining letters, the underscore, and numbers. And all special symbols are not included. Instead of doing, if we use \d, that's all digits. So 0 through 9, we don't have to type 0 and then a dash and then a 9. We are saving some keystrokes. And also it just helps us avoid mistyping character sets. We also use shorthand sequences specifically to match tabs, new lines, spaces. And the important one here, that was something that came up as a question earlier, which are the word boundaries, which is the \b. So let's get straight to word boundaries, because it can be cause for confusion. So word boundaries also, there are these things that match positions. So they will match whatever is between a word character, which is just letters, digits, or underscores, and non-word characters, which are either the ends, the starts, or the end of the string, and spaces. So let me just explain it with these examples. So let's say we have these strings, one just the word case, another string is the two words two cases, and then another one is suitcase. We add a word boundary and then the literals CASE. So this here, I guess it's an invisible, we can't see the word boundary, but the start of a string, that's a word boundary. So we're getting a match here when it's just case. The space here is a word boundary. So we're getting a match here. Or we can actually put a word boundary after our literal strings. So without having to specify, it can be anywhere in the string, not at the start or not at the end. We're matching org at the end of a word. So we're matching this here before the space, but we won't get a match if we don't have a word boundary right here after the org. Another quick reference is just the \w. That's equivalent to all letters, uppercase and lowercase, and all numbers. So if we want to match everything that's not punctuation or things like that, we use the shortcut \w. We will get accented characters because those are not, because those count as alphabetical A through C. It depends on whatever language we're using. I mean, human language. And let's just have a quick, I'll do a quick demonstration of the behavior of word boundaries. So this is just a single string. The atmospheric sensor is at the university. I'll put that in my tester. Sensor is, put that in my string, and then just see, we have the literal strings A and T. Let's try that out. And we're getting a match every time this thing appears. But we can actually see what happens if we add a word boundary before. So in this case, we're only matching the literal string at when it's at the beginning of a sentence. So atmospheric, or just the word at. And if we move this word boundary, now we're getting the match at the end of a word. So I feel like that's pretty cool, especially when we're working with human text that has spaces and they're just sentences and things like that. We can use word boundaries quite flexibly to do things and save time. And let me just show you a few combinations. So for example, we can have a start anchor, which is the little hat, and then we have CAN, then a dot, which is the wildcard, and then a quantifier, which is the asterisk. So we'll match. There's a mistake here. We'll match pretty much anything that starts with CAN and then whatever, but not if the match is not at the start of a string. We can match, for example, any letter that starts with any word or any string that starts with a capital A, whatever's in between, numbers, letters, whatever, and then the letter X. Or we can do things like use a shorthand sequence, which is the \S, and then a 3. So we'll match, if we're looking for 3 spaces, we can look for that quite specifically by doing a combination of the shorthand sequence and the quantifier. Also combine, things like the to start and then an end start and end anchor, and just specify that we want A through C in lowercase using a character set. We use a quantifier so that we can match however many characters there are. So with this is something that we can use to match only lowercase strings. Any string that has no uppercase characters in them. And then again, this is starting to look more and more like nonsense. But if you actually just take a look at it, we have the shorthand for a word character. So any number of word characters, which are just letters and numbers or whatever, plus a quantifier, and we want this to be preceding at a word boundary at the end of a string. So basically, we're describing the last word in a string, or the first word in a string, depending on where we put the word boundary and the start or end anchor. So these things, we can just, things like Google for maybe the regular expression for the last word in a string, or the regular expression for the first word in a string, but we can also just build these things ourselves. I modified a concept map. Concept map that was originally produced by Greg Wilson. I think I have the original one somewhere. This is my variation. So I think this is a very, very useful summary of what regular expressions are and the different characters that we can use. So literal characters, they match themselves. But then we have quantifiers, we have character sets, very cool little printout that you can use. At this point, any questions? Or how I lost anyone, or I don't know, anything. If not, I think we're good. So I'll keep going with this, which is we'll move on to actually working with regular expressions in R. So here's a little illustrated example of a few things we can do using regular expressions. so that the font's a little small, but let's say, for example, we have this rectangular object that has a variable. In this case, it's maybe the variable that describes our observational unit. So it's called animal, and we have things like badger and a hog, and a crab and a frog. And we can define a regular expression to match these two things, right? So what we have an O and a G at the end of a string. And in this case, if this is a data frame or a table or whatever, each value here is a separate string, and then we can do a regular expression to match, or maybe you want to filter any row that has a match of whatever ends in OG. So we can do any filtering operation or any subsetting operation to save time, and we didn't really have to type out that much, and we kept the hog and frog. So that's something we can do to work with rows. We can also use regular expressions when we're trying to match column names. So let's say we have these variables, so x1, y1, x2, y2, whatever. We only want the ones that start with a particular letter or prefix or whatever. We can also use something very, very simple like start anchor, and use again any sort of selection function from whatever package we prefer, to maybe just keep those columns that include that start with an X. My particular preference is for the string R package, mainly because of this thing here. Well, it's two things that I like. So pretty much all functions from the string R package, which is a third-party package, it's part of the Tidyverse suite of packages. So it's things that play well together. But a thing that I like is that the main functions that we'll be using, they start with str_something. And also all these functions from string R, their very first argument is our string of the string that we're working with. If sometimes with the base R functions like grep or gsub or things like that, sometimes they'll ask for the string first, or sometimes they'll ask for the pattern first. And that's not a fault of their own. It's just something of how these things got built into R from their standalone command line programs. So this has just been rewritten. So everything in string R takes a vector of strings, or a string, as its very first argument, which makes these things more friendly with pipes. Again, string R also has a function called regex that we use inside string R functions that we can use to control matching behavior. So just like in the little online text tester, we have this I flag to make the matching case insensitive. In this case, we have an argument called ignore case that we can use to turn case insensitivity off or on. So it's something that I like, and it's just easy to read, at least in my opinion. So this is a very simple example with string R. This is a very useful function, str_detect, because it's essentially doing what we were doing in the regex testers. So we're just going to see if we have a match or not. The output for the str_detect is a logical vector, just true or false, of the same length as the input string. So this works with just character vectors, but it will also work on maybe a column in a data frame or table or data table. And the thing is, logical vectors are what we ultimately use in things like the filter function from dplyr if we want to subset rows. Let me just run this inside RStudio so that you can see. I'll make my font slightly bigger. Second. I'll just load string R in just a random script, and I'll run this thing where, as you can see, the first argument for the string R functions is always just the string that we're working with. In this case, we're trying to see which of these vector elements contain a match. We're doing a very simple pattern here. And we can see that the first and the second elements contain a match. These are the type of things that we could maybe use inside the filter function from dplyr. So it's not as nice as having a regex tester tell you in color, but it's something that we can actually use when we're manipulating data objects. So the strdetect function is a very useful one. We can also use a different one called strwhich that will do the same thing, apply the same pattern matching, but in this case, the output is just the index of the elements that contain matches. So the first and the second elements, so catalog contains cat, battle cat contains CAT, and we get the index for each one. There's a ton of string R functions for this. And now we can get to even some other useful ones like find and replace. So in this case, the function is strreplace, and the output is our input vector, but we've replaced any possible matches. So what we're doing here is we're replacing, at least for this particular case, British to American spelling, right? So we're matching anytime we have an O and a U together, replacing that with an O. And we can do that, for example, inside the mutate function from dplyr. So let me stop here and see if there are any questions about this. So I can get the chat going.
No questions yet, Luis.
All right. Well, any questions now about this or about anything from before? See a thumbs up, but I'll just give you a few more seconds in case anyone changes their mind and there's actually a question, but if not, I'll keep going. All right. So this is relevant to a question from earlier, right? So it's the same function, strreplace, but in this case, we're feeding our regular expression, which is just OU. It goes. I mean, in our all regular expressions, we type them inside quotes because they're strings. So in this case, we're putting our regular expression inside a function called regex that lives in the string R package. And we're basically only doing this so that we can use this argument here. So we're turning on case insensitivity. Basically like that little I flag that we put in in the other box in one of these testers. So what we're saying here is that we're matching O and U, and in this case, in this particular function call, we don't really care if it's lowercase or uppercase O and U. We're going to take those matches and then replace them with a single O. And we do that, and we get our same vector back, but with the replacement. I'm going to just demonstrate that quickly, and I'll turn on and off the case sensitivity. So this is just as it was in the slides. And if I change this argument to false, then I should get back my same input string, because we're leaving the matching to be case sensitive, right? So in that case, OU in different combinations of upper and lowercase are not the same thing as OU in lowercase. We're being case sensitive, so nothing's being replaced in our string. I feel like that's a cool little argument. That's a cool thing, a cool way to toggle case sensitivity without modifying either our regex or our input string. And another quick demo. So I'm going to copy this with a little button, and I'll paste this, and I'll just create this test vector here. So it's 1, 2, 3, 4, 5, 8 or 9 elements. Some are numbers, some have different combinations of uppercase and lowercase, and we'll just try and match these things against these 3 different regular expressions, and just see what's happening with them, with the matches. So I'm going to create my test vector. So it's there's 10 elements here.
Luis, you do have a quick question in the chat if you wanted to check it.
All right. Thanks for that, Crystal.
Yep.
Let me have a look. Why doesn't the D work? I wasn't aware that it wasn't working. So let's, or what is this question in relation to? This particular demo?
I couldn't get that one to work in R. I only got that one to work in the online testers.
So you might have to, as I was saying earlier, just escape the first backslash so that it becomes the shorthand notation. So you might have to double up on the backslash. So just do 2 instead of 1. And that might work. I just haven't gotten that far yet. But let's just try it out. So, okay, so that fixed it. Yeah. So I mean, when I put the regular expressions here, they're not in quotes. I didn't escape the first backslash. So these things are not that ready for direct use inside R. But let's just try it out. So I have a test vector. I'm going to just use str detect just to get a logical vector. My first argument is always my input string, so I don't even have to name it. Test vector. And my second argument is my pattern or my regular expression. I'll just quotes. In this case, I'm looking for dog at the beginning of a string. And I see that there's at least one element here that contains this pattern, which is the second element, which is, yeah, it says dogs and cats, and the DOG are at the very start of the string. So we have I can try again. I'll switch function to str which, and it tells me indeed that it's the second element that contains a match. Does anyone remember what this second regular expression did? Or without running this, can anyone tell me which of the elements are going to be a match? Or at least in any of these elements, will there be a match? And while you either have a think or just try it out, I'll just go over what's happening here. So remember that the little hat, that's a start anchor. And then we have an end anchor, so we're matching the entire string. We have a character set, so it's just everything from lowercase a to lowercase c. We have a quantifier, so we can do either one or more. So as if you remember, that's this is a regular expression for lowercase strings. And there are a few items here that are just lowercase strings. So that's what we're matching here, and we should get some answers here, which I think Crystal got it right. And Martin also had that one. Let's just run it. Swap out the regular expression. And I'm getting that, just having to read the logical vector, just the index. I think there's a function that will just so another function that I think is not on the slides, str extract, will actually extract the matches. So as Crystal had said, we have rat, watchdog, placemat, and mice. And the other vector elements, those have no matches, so we get back NA, at least for this particular function. And then the last one in this little demo was the shorthand for digits. So let's just do that quickly. And I'll just do it with a pipe so that you can see how it's pipe friendly, because the first argument is the test string. So if you're unfamiliar with pipes, what we're doing is that instead of we're piping, or it's a notation to put whatever's on the left-hand side of this symbol here, which is a pipe. It's going to be placed as the first argument of the function on the right-hand side of the pipe. So all we need to type here now is our regular expression, which is the shorthand for the digits. I'm using double backslash. There's some of these say true, so there are some matches. I'll use test extract. And it pulled out the numbers from, actually, let me do extract all. No. I don't want to confuse anyone. So I'll do str which. So element 3, 4, and 9 contain numbers. So 3 is this one, 34. 4 is this one, it's 34 but in brackets, and then the 9th element also includes digits. So that's what we were able to match using the shorthand notation. And now just let's do a more applied, at least go over some demonstrations or examples of actually using regular expressions to manipulate data. As I had mentioned earlier, we can use that to do subsetting operations like selecting, or keeping rows, discarding columns. We can recode values, we can do substitutions, we can get rid of substrings. So I'll just do a quick overview of this. I am a tidyverse person, I guess. I prefer working within the dplyr package for data manipulation. And in this case, let's talk about the process of subsetting variables or columns. And in general, so with new developments, not even that new, we can refer to columns or variables using dplyr and tidyr and things like that. We can either write out their names, refer to them by position, so by index. So a 1 for the first column, a 2 for the second column. We can specify ranges, I don't know, maybe the 3rd to the 6th column, consecutive variables like that. Or we can use helper functions that come from the tidyselect package. I'll just explain, but these tidyselect helpers that I was mentioning, I was doing so because there's one in particular called matches that actually accepts regular expressions. So we can use regular expressions to match variables in our rectangular objects like tables or data frames or data tables. We can actually match, we can describe patterns using regular expressions, give it to the matches helper function, and then use that to subset columns quite flexibly. So this is just, there's a very nice data package called Palmer Penguins. It comes with an object called penguins. I'll run this just to show you. You feel free to follow along if you have this package. Feel free to install it. If you don't, it should be a fairly quick installation. So I'll load the package. And I'll just have a look, or I'll just do it here. I printed out the variable names for the penguins object. Name, penguins. Let's actually get that. So it is a table. It has a bunch of rows. It has 8 columns. We'll materialize that in my environment. You can look at it in the viewer. We have a species of penguins. We have the island where it's on, and then some measurements, some other variables. If for whatever reason I'm only interested in lengths, so things that someone went out and they measured these penguins and they took the length of the bill and of the flipper. I want to just select species, bill length, flipper length, and then just for space reasons, I want to show 3 rows at random. This is one way to do it with pipes. So I'm using the select function from the dplyr package. I'm subsetting these 3 columns by name. And then I'm piping the output of that to the sample n function, also from dplyr, to get this little 3x3 table. I'll just demonstrate that just quickly, make sure it works. I guess I need to load dplyr for that. And there we have another random selection of rows. So as I was mentioning, I was, for whatever reason, only interested in columns or variables that contained length in their names. So I could use the matches helper function to go ahead and look for these things. Maybe, for example, we have a huge table and it has just not 8 variables, but hundreds of variables, and only some of them might have a pattern of interest for us. So we can use the matches function inside the select function to get at this. So we want our species, so we just type it out by name. We could also do that by position, by index, and then we'll just get anything that matches length, right? And whatever goes into this matches function can be a regular expression, not just a literal string. So that's a very cool thing to do. We can use wildcards, we can use quantifiers, we can use whatever inside the matches function. So let's just do that. We get the same output. Well, not quite the same because the rows are sampled at random, but in this case, it saved me some typing. But it can be helpful in other cases when we have lots of columns or we want to match a very specific pattern. So that's one way we can use regular expressions to subset column names. This is an example with a separate data set. It's the mSleep or mammalian sleep data that comes from ggplot2. Just as an example, we're selecting the name of the mammal, and so the common name, and then just the genus, right? This is just a quick sample of how it works. So let me try that out. I guess I need to load ggplot2 for that. And we get random sampling of 4 rows for them. Give me 2 seconds. Sorry about that. So we were at this, so we were doing just filtering some rows. Let's try and do a combination of 2 things, right? Let's, from the mSleep object, let's just keep the common name and the genus. We have some, and then we're actually going to subset rows. And in this case, we're using a string art function inside the filter function from dplyr, which in itself expects a logical vector. Because as you know, the filter function, we can use that to maybe filter rows according to the value. We can do things like, let's keep only values greater than or smaller than or equal to or identical to whatever. But we can also use regular expressions through the string art package. So in this case, for example, what we're doing is we're going to keep only the rows for which the common name variable includes the string rat. When we do that, we should get this table, which is just 2 columns, 5 rows, and it's only these different types of rats. So just going to try that out, make sure that works. right, we have our 5 different species of rats. We used a fairly simple regular expression here, but now if anyone is willing to try this, so running the same code from before, right? So we're just selecting name and genus from the msleep data that comes with ggplot2. We would get this output. How can we exclude the muskrat from our matches? So I'll give you some time to attempt this. I'll open my chat. Also, if there are any questions, feel free to ask them at this point. All right, we have a suggestion here from Crystal. Would you care to explain that your suggestion?
I can't remember. I think it's /B is the word separator. Anyway, nothing before rat is what I was trying to go for.
All right, so let's try it out. So if I keep my regular expression or my pattern just as rat, I'm getting these 5 rows. I don't want the muskrats. So following Crystal's suggestion, if we do a word boundary, right? So we want the RAT pattern to be immediately after a word boundary, and spaces are word boundaries. So this should actually work, and it did. So we did exclude muskrats from the subsetting operation, and I don't know if anyone tried anything different. To get the same answer. So for that, we just have a look at the other input. So we have, laboratory space rat, cotton space rat, mole and then rat, pouched and then a space and then rat. The word boundary approach is the one I would have gone for. Megan is saying that she would just type muskrat like a savage, maybe in a second filtering step. That's fair enough as well. In the interest of time, I'll just show another. It makes sense and it feels like cheating, but we can do something like put an actual space in the pattern that we're looking for. And again, we're also excluding muskrats from that. So we can have spaces, even if we can't see them, it's a character, it's there. Maybe I wouldn't recommend doing this because sometimes depending on font sizes and people's eyesights, we can't actually see the spaces. So maybe the word boundary might be a good approach, or actually using a shorthand for space. So the double backslash and then an S. And that also gets us at the same result. So it does save some typing. This is a very somewhat silly example, but I personally, I work with rodents, and there's 2,500 species of rodents in the world. A lot of them, their common name includes rat or mouse, or various combinations. So I have used these particular approaches in practice in my own work, and it does save time if you can learn to describe patterns, and then just rather than have a whole bunch of operations or a whole bunch of options and things like that, a single well-written regular expression in this argument here can save a lot of typing and time and trying and things like that. So let me go back to my slides, which I think we're good with the time. That leads me to just some wrap-up thoughts. So in my opinion, learning regex, super helpful. Second thing, we don't really need to write regular expressions from scratch. We can just look for them online. Some of the regex testers that I mentioned, they have little guides there. I think regex 101, if you create one that you like, you can save it there, and then other people can access that. So I guess at some point we learn how to do web searches that describe the pattern that we want to write as a regular expressions. So it's good to know about things like what the dot is, or what the question mark does, or what the plus sign does. But we don't really need to write these things from scratch. It's useful to know, and it's useful if we're reading other people's code like that. I haven't tried this at all, but these new language model, artificial intelligence things, they can also write regular expressions. I'm not sure how well it's done, but at least I'm happy to be able to interpret someone else's existing regular expressions. Also, there's a few features from regex that I left out, mainly because they're a bit more complicated, and then their use cases is more limited, and it's not very general, but things that you might run into at some point that I want to leave in the slides for this are things like look aheads, look behinds, things like named groups or capturing groups or back references. Those things are things that I've used sometimes, but a lot of the time we don't really need them. But it's something that some terms that I want to not ignore from this material. And thank you all for attending. Thank you for your questions. Thank you for participating. And we do have some minutes, I think, for some questions or comments.
Yeah, I'm going to go ahead and stop real quick the recording.